Most artificial intelligence models work by simply answering a question once it's asked. However, newer models, known as large reasoning models, LRMs, try to impress by showing their step-by-step thought process before providing an answer. It may seem like they're thinking through the problem in pieces, but here's the twist. Until now, nobody has really checked whether those steps actually make sense. As long as the final answer was correct, we just assumed the model reasoned its way to it. But what if that's not the case? What if it's merely piecing together familiar patterns from its training data, giving the appearance of thinking when it's actually faking the whole process? Before we dive into that, mark your calendar. This Sunday at 4 p.m. Eastern, we are premiering our first full-length documentary, and trust me, you won't want to miss it. We've spent months tracking down some of the most advanced humanoid robots on the planet, many of which you've never seen before, on our channel or anywhere on YouTube. You'll get to see Chinese robots doing backflips while loading cargo, Japan's sword-swinging androids, a Polish robot made of artificial muscles, and a Russian robot so human-like it might even haunt your dreams. And that's just the beginning. It's dramatic, intense, and honestly, a bit unsettling. So set a reminder, grab a seat, and witness the world's most advanced humanoid robots this Sunday at 4 p.m. Eastern. Now, Apple's research team wanted to clear up the confusion around whether artificial intelligence models are truly capable of reasoning. To do so, they conducted experiments using puzzle-like environments, familiar to anyone who has studied computer science. These puzzles included Tower of Hanoi, checkers, jumping river crossing, and a challenge called Blocks World. What makes these puzzles ideal is that their difficulty can be increased gradually while keeping the underlying logic the same. By adding more discs in Hanoi, more pieces in checkers, more agents in river crossing, or more blocks in Blocks World, the complexity increases in a predictable manner. This setup allowed the researchers to simulate every single move the models made, providing an opportunity to evaluate not just the final answer, but every step taken along the way, up to 64,000 tokens worth of reasoning. And because these puzzles were newly created, there's no risk that the answers had appeared in the training data, ensuring a clean test. For example, in the Tower of Hanoi puzzle, if you begin with 8 discs, the shortest correct solution takes 255 moves, and with 10 discs, it jumps to 1023. In checkers, jumping with 2 colors and n pieces each, the minimum number of moves required is n plus 1 squared minus 1. The river crossing puzzle starts with small groups using a 2-person boat, then increases in complexity by adding more pairs and a slightly larger boat. These puzzles become more difficult in a predictable way, allowing Apple to precisely dial in the challenge level to properly test reasoning. They compared 2 models with the exact same architecture, size, and weights, the only difference being whether the reasoning feature was enabled. They compared Claude 3.7, Sonnet with and without thinking, and DeepSeek R1 trained to reason step-by-step versus DeepSeek V3 standard version. Both versions were given the same token budget, 64,000 tokens. Each puzzle was run 25 times to minimize randomness, and they tracked metrics such as pass at K, which measures how often the model got it right within a few attempts, as well as how many correct steps it took and how much thinking it actually did. Here's the surprising part. In each puzzle, the results split into 3 distinct categories based on difficulty. In simpler puzzles, the non-reasoning models performed better. They gave quick and correct answers without wasting tokens. In puzzles of moderate difficulty, like Hanoi with 7 discs, the reasoning models started to outperform the others, although they needed more tokens to get there. However, when the puzzles became truly difficult, all models, whether reasoning or not, collapsed. Their accuracy dropped to 0. For instance, Claude 3.7 thinking handled up to 8 discs in Hanoi, but when it attempted to go through 10 discs, it failed. DeepSeek R1 gave up even earlier. When they tested Hanoi with up to 20 discs, over 1 million moves, none of the models could handle it. The same pattern appeared in other puzzles, such as checkers, when it needed 11 or more jumps, or in Blocks World with larger stacks. One of the most unexpected findings was how the models handled their internal reasoning efforts. You might expect that as difficulty increased, the models would put more effort into reasoning, but that's not what happened. At first, as difficulty increased, the models thought more, but once they hit a certain level of complexity, their reasoning efforts started to drop, even though they still had plenty of tokens available. Apple referred to this as a counterintuitive scaling limit. So you'd see DeepSeek R1 using up to 15,000 tokens on a moderately difficult puzzle. But when the puzzle became even harder, the model would drop to just 3,000 tokens, even though it could have used many more. This drop in effort corresponded with the drop in accuracy. To dig deeper, the researchers handed the models the full solution for the Hanoi puzzle, written out in simple steps. The models didn't need to figure it out. They just had to follow the instructions and replicate each move. But that didn't help. They still broke down at the same points. This shows that the problem isn't about solving the puzzle from scratch. It's about executing a logical sequence over many steps. Claude 3.7. Thinking could complete about 100 steps correctly out of the 1,023 needed for 10 disks, but failed afterward. In the river crossing puzzle, it failed after just 5 or 6 moves, even though the solution only required 11 moves in total. This wasn't a memory problem, it's a failure in symbolic reasoning. When the research was published, many in the AI field had a lot to say. Gary Marcus, a longtime critic of neural networks, called the findings devastating. He reminded everyone that back in 1957, Herb Simon had already created a working solution for the Hanoi puzzle, and today you can find hundreds of working algorithms online. If AI models can't even follow these, how are they supposed to reason? Some responded differently. Kevin Bryan from the University of Toronto suggested that Apple may not be exposing a weakness in intelligence, but rather a design choice. These models are often trained to avoid overthinking simple queries in order to save time and reduce server costs. He believes that if given more space to think and more tokens, the models would perform better. It's not that they can't solve harder problems, it's that they're trained not to try too hard. Software engineer Sean Godke made a similar point, suggesting that when DeepSeek saw that a puzzle required 1,000 moves, it likely realized it would run out of space and didn't even try the full sequence. On the other hand, artificial intelligence researcher Simon Willis argued that using Tower of Hanoi to judge reasoning may be missing the point, as language models aren't designed to be step-by-step machines and may never match the efficiency of a proper algorithm. Even Apple's team admitted that the puzzles they used represent only a small part of what reasoning means. However, the reason these puzzles are still valuable is that each move can be tracked and verified. This makes it easy to spot when a model's so-called reasoning fails. Researchers found that in easier puzzles, Claude would often get the correct answer early in its thought process, but waste time chasing incorrect paths afterward, essentially overthinking. In more difficult puzzles, it would often start with wrong thinking before eventually finding the correct answer. And on the hardest puzzles, the correct answer never appeared at all, not once throughout the entire 64,000 token reasoning sequence. This shift, from getting it right early to late to never getting it, was consistent across all puzzles and was clearly shown in the paper's Figure 7. Jumping from that lab setting to Monday's Worldwide Developers Conference event in Cupertino, you might have expected Apple to unveil something groundbreaking in artificial intelligence, given all this research. Instead, they focused on design. Their new liquid glass look, which they're calling the biggest redesign since iOS 7, is all about translucent buttons, fluid animations, and curved glass-like elements across iPhones, Macs, and even the Vision Pro headset. Craig Federighi showcased how Apple Silicon is now fast enough to render these effects at 120 frames per second. The animations are beautiful, but Wall Street wasn't impressed. Apple stock dropped by 1.2%. One analyst pointed out that the AI features shown weren't new and were already available in other apps. To be fair, Apple did demonstrate some AI features, just not the kind that grab headlines. They introduced a new real-time translation feature for phone calls, where two people speaking different languages can have their voices instantly translated without a cloud connection. They also added a button to screenshots that allows you to send an image to ChatGPT for summarization. You can now use ChatGPT to generate images directly inside Apple's photo apps. However, the big Siri upgrade they teased last year, the one that could scan your emails and automatically schedule things for you, was missing. Apple says it needs more time to meet their quality standards. Meanwhile, Apple's researchers were tackling deeper questions. Their study even tested OpenAI's 0.1 and 0.3 mini models, which hit the same barrier. They performed well up to about 8 disks in Hanoi, but completely failed by 10. This was consistent with findings from the United States Math Olympiad study earlier this year, where these models scored below 5% on brand new math proofs they hadn't seen before. Only one got 25%, and none scored perfectly. As long as the solution already existed in their training data, the models did fine. But when faced with a truly new challenge, the illusion of reasoning starts to crumble. Lastly, Apple ran math benchmark tests on the same models, DeepSeek and Claude, with and without reasoning, using the popular Math 500 dataset. Both versions performed similarly when allowed to try multiple answers, but with newer test sets like AIME 24 and 25, the reasoning models performed better. Interestingly, human test takers actually did better on AIME 25 than on AIME 24, while the AI models performed worse. This suggests that older test sets may have leaked into AI training data, artificially boosting their scores. Therefore, the newer tests revealed what the older ones had concealed. One more curious detail: Claude 3.7, thinking could perform over 100 correct steps on 10-disk Hanoi before making its first mistake, but in the river crossing puzzle, it broke down after just 5 moves, even though the total solution required 11. This suggests that there are many more examples of Hanoi puzzles online, especially for 10 disks, whereas river crossing puzzles with more than 2 pairs of people are rare. As a result, the model had fewer examples to draw from. What we're seeing is not real reasoning. It's where pattern recall stops working. So, is it fair to say artificial intelligence is fake? Perhaps not in the way people usually mean, but Apple's research does show that current AI models can't truly reason through long, complex tasks. Their thinking falters when the challenge becomes too difficult. Some researchers believe more tokens and better training can fix this, while others argue we've reached a wall and need a new approach altogether.